Hello, hello, Rachna. Wait. We'll start at 1:05. Hello, hello. Am I audible? Uh, Hello, everyone. Uh, Today, this is going to be our last session in summer school. Thank you, everyone, to supporting us till now. I am Kisle Bharti from Horizon, and today, me and my team is going to present you about gravitational wave and the LIGO. So, uh, with me, Avinash, Ashim, Rachna, and Mridula will be there, who will be conducting this session, and we'll start. So, first thing, anyone have idea what is gravitational waves and LIGO? You can write in the chat if you have any prior knowledge or something like that. Okay, fine. So, uh, so for those who don't know, so gravitational wave is just a disturbance, but in what, if you think? in what the disturbance wave is nothing but a disturbance in the medium, but what medium we are talking about. So here medium or material through which gravitational wave flow through is space-time. I think you have heard this term space-time before if you are physics and astronomy enthusiasm. But for today, we will talk about this not very briefly, and then we'll go how the gravitational wave comes. So before going to talking about these things, let's talk about why we need gravitational wave on the first place. Why we need gravitational wave? Oh, before that, I will explain the content, whatever the content we are going to cover today. First, we will talk about gravitational wave. Then we will go through brief overview of the theory of relativity, that from where gravitational wave came. After that, we will go to the historical journey of the gravitational wave. Then how do we detect gravitational wave and the future of the gravitational wave detection. So this is going to be very brief content what we are talking about today. So first thing is that why we need gravitational wave on the first place. Any idea? You can write or you can write in the chat. So first thing is that we as a human are very curious about our universe. We want to know about our universe, how these things happens. So we need a lot of data and information uh, from outside Earth. So how we get the data and information? The major source is electromagnetic waves till now. Uh, I think all of you are college students, so you know that what is electromagnetic waves in general. So they are just electric field and magnetic field that are oscillating with each other, and they are generated by charged particles like electrons in atoms and all. So these electromagnetic waves gives us information about stars, galaxies, how what are the composition of stars, what are the processes that is happening in stars, galaxies, and all that stuff. But they lack something. Uh, as we know that electromagnetic waves are can be distorted or can be easily disturbed. So these waves can be cannot escape from the inside of black hole. They didn't give us information about those things in the very early when electromagnetic waves are there, but its mean path time was distance was very low, so they didn't in the opaque universe in the very start they didn't give us any new information about. So we need an alternative of that so that we can get information more about our universe. So here comes the rescuer gravitational wave. So as the so gravitational waves basically are generated by moving masses. So any mass matter present in our universe, and if it is moving or accelerating, it will generate a gravitational wave. So that's and the let's talk about from where they came. So they are from a black hole merger. Electromagnetic waves didn't give a lot of information on black holes, but this gravitational wave, since they are produced by them, they give us information about that. Neutron star collision. We'll talk about neutron star. What is neutron star in detail after this in our session. After that, supernova. They give us information about this. The supernova core is kind of opaque to electromagnetic wave, but gravitational wave can penetrate through them. They can tell the information about that. And next is even possibly from the Big Bang. Since gravitational wave is coming from that uh, mass space-time interaction, they can even give us information about the Big Bang itself. Because in the very start, a lot of energy, that energy is nothing but some sort of mass. We can interchange using the uh, E equal to mc square Walla formula. So yeah, it can even give us information about Big Bang. So this is why we are going to study gravitational wave. So the perks of gravitational wave using gravitational wave is that they didn't interact with matter so much. So they are just clean and direct information from that side. So whatever information it is given to us is clean and direct. So this is whether where in for electromagnetic waves it is not. For electromagnetic we have to filter a lot of stuff, noise cancelling, and a lot of mechanism has to be done for electromagnetic wave. But even for gravitational, if you think there are limitation to you, you have gravitational waves are very very weak. You need very sensitive setup to know that where gravitational wave is there or not. So yeah, these are the perks and limitation of the gravitational wave. Now you get the idea of from what why we are going to study about gravitational wave. Let's talk a little bit about uh, the mother theory of gravitational wave. That's the theory of relativity, special and general relativity that was given by Einstein. So yeah, I think a lot of people have seen this field equation, but we I just don't want to talk about this because it is very deep and still I don't have any technical knowledge about this in detail. So we can talk about how what this equations tells. So the theory of relativity tells us that uh, in Newtonian mechanics, you will see that there is something called gravitational force. In Einstein theory, he suggested that gravity is nothing but just interaction of matter and space-time. So whenever so how they interact, matter will tell the space-time how to bend. Once a matter is in our space-time, it will curve or depress our space-time, and the space-time will tell that how the matter will move in that space-time. And the action that thing how to move is nothing but we are observing it as a gravitational force. So this is what Einstein told us. Next, we'll move to why we need. So we are going to talk about theory of relativity, but why we need that? What's the use of theory of relativity? Can anybody tell? Before that, there are a lot of theories that was proposed, but what's the flaw or wrong in that we need another theory to explain things? Any? There are a lot of flaws before that. Can anybody tell? Okay, Mercury orbit, nice. One of those things. Any other? Okay, so we'll talk. So first thing, before Einstein, people used to think that if there is a wave, it needs medium to travel. And since light is also a medium, if you think light is my bad, light is also a wave. It will also need a medium. But we know that sunlight is coming from sun to earth uh, without any medium. There is a vacuum inside it. So before Einstein, scientists hypothesized that there is something called ether that is present everywhere in universe, even in vacuum. So what they think that light used to travel using these ether medium, but so it's not like we give a hypothesis and tell this is true. We have to do experiments and we have to tell that whether it is right or wrong. So a lot of experiments has been done, and that states that there need not to be a ether and vacuum is vacuum basically. So one of the experiment that we that was very famous for this doing was experiment. So I will give a brief overview what is Michelson-Morley experiment. What this experiment tell us that uh, see our Earth is in space. So they tell that if ether is there, ether wind will be there. So if our Earth is rotating with the ether wind, then it's more like wind is going on. You have a ball, you are throwing a ball. So if it is in the same direction of ball, it will have some other velocity, and if it is against that wind, it will be have other velocity. Does that make sense? Fine. So they tried to detect. Ch- they tried to calculate experimentally check the uh, velocity of light using this. So what they did is they took two three different direction and they tried to check the speed of velocity using interference pattern. But what they get was no matter what the direction is, speed of light is constant in everywhere. So they come to conclusion that there need not to be ether. So there are a lot of experimental data and experimental information that tell that we don't need ether to explain propagation of light. But there was not a proper theory part that can explain this. So this was one of the flaw before theory of relativity. Second flaw is inconsistency in with Maxwell equation. Newtonian, you know that Newtonian relativity. So Newtonian relativity tells that if you are moving with someone, your velocity will increase or decrease. Your frame of reference in your frame of reference, the velocity of other thing will increase or decrease depending upon the in what direction you're going. But in Maxwell equation, when you go and see that the Maxwell value of c doesn't depend on frame of reference. It doesn't matter in what direction you are going. The speed of light will be constant. In what direction? Not my bad. In what frame of reference you are in. So the Maxwell equation was inconsistent with the Newton. So these are two major theories that was at that time, and they were inconsistent with each other. It means that we need a better theory that can explain things in a better way. And as one of our viewers say, that audience, so that uh, wait, uh, Mercury orbit trajectory. When we try to explain the orbit of Mercury using Newtonian gravity theory, you won't be able to explain it properly. So for this, to explain this, a lot of scientists come with very different techniques. They very different ideas. They say that there may be some different planets in other side of sun that can change the orbit of trajectory, and a lot of different stories and different ideas. But nothing was not fitting with the experimental data. So yeah, so these are the things. These are the major things that led to the scientific community to tell that we need a better theory to explain things. There are a lot of others we can talk, but these are the major. So now, once Einstein come up with theory of relativity, special and general both, now it's time to prove it whether its theory is correct or not. So this is the only thing. Now, you have an you have this is what physics do. This is what science has to done. First, they will explain things that they wanted to. They theory and theory gives some kind of predictions, and it has to fulfill with experimental data. Are you understanding? Yeah. So we have a theory now. It will make some kind of predictions, and using experiments, we'll check that whether prediction was correct or not. That will validate the validation of theory. So let's jump into this. Some sort of uh, prediction that relativity make. The first thing they make was time dilation. I think you have seen some this formula somewhere if you are in college and you are physics enthusiasm. So what this does was it will tell that if your frame has some kind of if two frames are in uh, relative motion, they will experience time very differently. So this is how you what will be change in the time for both of them. So delta t equals to gamma, where gamma is nothing but 1 by root under 1 minus v square by c square delta t naught. So this is how time will be in two frames. So talking about experiments, what they did was, muon. Muon is a high velocity particle that will reach to Earth. So so ideally, when the muon will reach in the Earth's atmosphere, it shouldn't reach the its decay time is very low, that it shouldn't reach Earth's ground. But what we see that it reached our Earth grounds. Our experiment was not telling why it is happening. So what we did was we since muon is moving with near the velocity of light, it has some other frame of time dilation will happen with the muon, and they instead of decay, their decay time will increase. So they can reach Earth even their decay time is very less, according to that was predicted by Newton. So yeah, this was one of the experimental proof that say that it was correct. Next was length contraction, that was almost same, and there are a lot of experiments that prove that it is correct. Next come gravitational lensing. So what is gravitational lensing? So basically, I think everyone is familiar with geodesic. What is geodesic? So for those who are not, so basically geodesic is nothing but shortest path from one point to second point in any space. As for example, if you want to go from uh, India to call Germany, so you take aeroplane. So we will go in the geodesic. Even you are going straight, it is not straight because our whole Earth is spherical. So it will move from one place to another in the shortest path that is not straight line. It will some kind of arc. So this is geodesic. So geodesic is gonna, if you're going from one point to another, it will follow the shortest path. And for light, light always follow the shortest path in space-time. So it will always follow from one place to another using the space-time, and it will be very, it's the property of light that it will follow the geodesic in space-time. So what is gravitational lensing? It's more like this white dwarf you are seeing on the screen. Consider it as sun, satellite is Earth. Now what we uh, near the sun, you will near the edge of the sun, you will see that there will be some starlight that is coming. So as the star is coming, starlight has to follow the geodesic. It will follow the space-time. So it will not be straight because space-time is curved. So it will also get bended because it is following space-time. It's more like uh, you have a mattress, you have some kind of grip, call it grid. You're marking everything. You're marking each and every grid with your pen, and the shortest part, whatever comes, is following the light. So yeah. So when you observe the Earth from Earth, that position of star, it will get sort of bend and apparent star position you will see from this direction. But once you reach from the other side, since the Earth is revolving around the sun, it will go on the other side. So on the other side, you can see the star position, real star position. Now, once you have apparent star position from the two different directions, you can tell that how much deviation is going to happen. And experimentally, you can tell that what is the difference between those two stuff, and the whatever value you come up with, that well that was made, that thing was predicted by the relativity and was correct. That was given by relativity. So this was one of the other prediction that relativity does. Other thing is geodetic precision. So in geodetic precision, what happens was in Newtonian gravity physics. So space-time is flat. So what will happen if sun is in the middle of this thing, and there is a gyroscope? Gyroscope is nothing but some tool that helps in understand the angular momentum. So since gravity is acting in perpendicular in the center, gravity is a central force. It will be acting perpendicular to the angular momentum. So while moving, you will see that revolving around this mass, you will see that angular momentum is always perpendicular to the central force. So angular momentum didn't get any torque. The torque, so momentum will never change, never get changed. So the angular momentum direction, the value direction of angular momentum will always remain constant over the whole thing. But what Einstein predict was different. Since space-time is bent, the angular momentum, what angular momentum, direction of angular momentum will also differently change because space-time is curved. So it will be a little bit tilted, not perpendicular, tilted. So while moving, the tilt will always change the direction of the angular momentum, and it will. And when we did the experiment using, I think Gravity Pro B, we did experiment and find that yeah, angular momentum direction was changing. Direction of angular momentum was changing, and it also the relativity theory of relativity that was given by Einstein. So these are the experimental proofs that tell that theory of relativity was good, was correct. Now, once we know about these predictions, there are a lot of other predictions that was made by relativity. That was one of them is frame dragging. You can go and search and see, and a lot of other. So now come the main point. Why we are talking about these things? The thing is that wave was also predicted by theory of relativity on the first place. So the thing is that uh, so gravitational was there is an interesting story that I want to tell. In the very start, we when we are doing maths and calculating using theory of relativity, we get a gravitational wave. And in the very start, scientific community did the calculation and they see that gravitational wave didn't have any energy. Energy of them was coming zero. So they see that there is no any physical meaning of this. So they skip this part and they think gravitational wave doesn't have any physical meaning, doesn't concern us now. But later on, when the computation become better and all things, they see that gravitational wave consists of some energy. So there has to be some physical meaning, and later on they explore that part And I will ask Avinash to tell that how they explore the gravitational waves and how they come up with this detecting stuff. So Avinash will take on and tell you about the historical background of gravitational wave. Avinash, you can take.
Okay. Hello everyone. My name is Giavnash, and till now, Kislev bro said about why what is gravitational waves, and why we are learning gravitational waves, why we need to learn, and about uh, general relativity, why we need them, and so on. That. Now let us look at the historical journey of gravitational wave. It will be in three parts. First one is the Einstein's prediction of gravitational wave. The second part, Hulse-Taylor binary pulsar. And the third part, the first direct detection of gravitational waves. Let's look at the first thing, Einstein's prediction of gravitational wave. We all know that matter tells spacetime how to bend, and spacetime tells matter how to move. Let's take a look at this picture. If you consider the ball as a star and a rubber sheet below as spacetime, the ball will bend the sheet. And if we add another ball like the smaller one in the picture and throw it like this, then it will go around and around in the bended sheet. What we know is the mass is a star and smaller mass is or Earth or every planet. So the bigger mass tells the sheet how to bend, and the smaller sheet tells smaller mass how to move. That's where the quote comes from. Matter tells spacetime how to bend, and spacetime tells matter how to move. Now take a look at the first statement. Matter tells spacetime how to bend. After said that quote, Einstein had a doubt, like what happens to the fabric? Sorry, Einstein had a doubt. What happens to the fabric if matter moves suddenly? Here is two pictures. In the first picture, we can see a ball is in still and the fabric is somewhat bent. And what if that ball suddenly moves? That's where the waves come from. And when it suddenly moves, the fabric will ripple in backwards or something, and they produce some waves. That's what Einstein predicted, and he did some math and described and proved mathematically using the linearized Einstein field equations. Here he proved it mathematically, not physically. So after Einstein predicted, every scientist wanted to know about this, and uh, some scientists didn't believe that gravitational waves existed. So uh, okay, let's just go to the properties that Einstein predicted. He said some properties of gravitational waves. So let's see the properties. The first one is speed. Gravitational waves travel at the speed of light. Yeah, at the speed of light, they travel through the space-time fabric at insane speed at the speed of light. And they carry energy and momentum. We will see it how they carry how the energy comes for the gravitational waves. We will see them in later. And what happens if pass through matter? When gravitational waves pass through the matter, then matter gets stretched and squeezed. But gravitational waves doesn't change at all. The matter will stretch and squeeze. Remember this point, because it is the main point. What is LIGO? We will see it later. And gravitational waves doesn't change because they didn't absorb or scattered with the matter. Next, it is obeys inverse square law. Its amplitude obeys inverse square law. For example, if we take a look at the light intensity, it is inversely proportional to the square of the distance. For force of the electricity, for force of gravity, for all, they are all inversely proportional to the square of the distance. Likewise, gravitational wave's amplitude is also obeys inverse square law. It is also inversely proportional to the square of the distance. And similarities for other waves. Like other waves, it also has amplitude, it also has wavelength, it also has frequency, everything like that. That's it for properties of gravity. Our first part is over, and the next part, Hull's-Taylor binary pulsar. From the heading, we had a doubt. What is pulsar? Is it a bike company? Of course not. We are not talking about any bikes here. Before we go into the pulsar, we need to go through the following. First one, the death of a star, and the next one is neutron star, and then the pulsar, and the main thing, indirect detection of gravitational wave. Why it indirect, we will learn later. First one, the death of a star. Now there may be some of you doubted that does star die? Are they live a life? Of course, yes. Stars are born, they live, and eventually they will die. If we go through then it will deviate from our main topic. If we go through the birth of a star and leaving of a star, it will deviate from our main topic. So I don't want to go through that. And we need to know about three main questions. First one, what does a star mainly contains? A star mainly contains hydrogen atoms and helium atoms and some traces of heavier elements like carbon, aluminum, and iron or more. Now, next question. What is the fuel and how does a star generates energy? We all know the nuclear fusion. I said star mainly contains hydrogen and these four hydrogen atoms combine to become a helium atom and releases some energy. That's what we call as nuclear fusion. All stars, almost all stars generates energy through this process. Next question. What happens after the hydrogen depletes? Like hydrogen depletes in the star. What's happened? It will enters into a new phase of its life. It completely changes. Let's learn what changes have happened. After almost used all of the hydrogen in the star's core, it will change its properties. According to the mass of the star before death, if the mass of the star before death is around 8 solar less than 8 solar masses, then it will become a white dwarf star. Our sun also will become a white dwarf star because it has less than 8 solar masses and 1 solar mass, sorry. And the next thing is neutron star. When a star before death it has 8 to 25 solar masses, then it will become a neutron star. And next, if a star is more than 25 solar masses before death, it will become black hole. I mentioned before death because some of you may heard about Chandrasekhar limit and TOV limits. Uh, let's talk about it. What is Chandrasekhar limit? It is the 1.4 solar masses. It's the Chandrasekhar limit. If a white dwarf star, I said star is dead, like all of the hydrogen scatters into space, like supernova or something. When it's happened, the core remains. When the core mass is less than 1.4, then it will remain as white dwarf star. If a core mass is greater than 1.4, it will collapse into a neutron star. Then what about TOV limit? TOV limit is at 2.5 solar masses. When a neutron star's core mass is greater than less than 2.5, then it will become a neutron star only. And if the mass is greater than 2.5, then it will become a black hole. That's about the TOV and Chandrasekhar limits. Okay, now we are. I don't want to go through the white dwarf star and black hole because they will deviate our topic. So I just want to go through the neutron star. I said 8 to 25 solar mass star die and then it will become a neutron star. The facts of the properties of neutron stars. It is densest object in the universe after the black holes. The fact is, if we take just a teaspoon of a neutron star mass, then it weighs more than the whole mass of Mount Everest, the tallest mountain in the Earth. Yes, that's how much dense is the neutron star is. And its magnetic field, it's a trillion times that of our Earth. Our Earth has like 65 micro Tesla. It is powerful enough to help us and shield us from the powerful solar rays. And just imagine, it's a trillion times more than that. That's how much the neutron star has the magnetic field. Also, its gravitational field is also that much. Just an example, if you drop an object from 1 meter on a neutron star, it will hit the surface with a velocity about 2.3 million meters per second. That's almost 0.8% speed of light. Ju- Just compare with it. If we take a ball and if we drop it from 10 meters, it will get 1 meter per second velocity at the surface. But in the terms of neutron star, it will almost about 0.8% speed of light. Okay, next its diameter. It is like few instead of despite of its mass and spin and magnetic field, it has only a few kilometers in diameter. Here is what almost 1.5 solar masses neutron star looks like when compared with the Delhi size. It's only just 20 kilometers in diameter. That's how dense and how small a neutron star is. But it way more than our sun. That's it for neutron stars. Next, pulsars. Reminder, it's not a bike company. It's a star. Some neutron stars are emitting radiation beams through their magnetic poles, like this one in the video, and which the neutron stars which are emitting the radiation are called pulsars. Like if our sight is on the lower side of the, like in in this video, if we are our sight is on the left side lower edge on the like image of video, then tick 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 all of my ticks are while we are seeing the beams of light. They are at regular intervals of time, and those beams are what we call as pulses. It's not this much slow, but it will weigh more than 100 times a second. And the thing is, they are so precise that we call the cosmic clocks. They are so precise, there is no such a thing as resistance to them at the space. So they are rotating almost forever, and they are so precise that our atomic clocks are also like not that much precise, but they are so much precise. And scientists uses these pulsars to know the properties of pulsars, like how speed it turns and how the orbital velocity of the pulsar changes, and that's all. Okay, that's it for our pulsar star. Next, the main thing, the indirect detection of uh, gravitational wave. See these two scientists. They are Russell House, the left one, and the Taylor, Joseph Taylor, on the right one. The two are go to Archivo Observatory and observe. While they are observing the sky, they found an unusual star system. That's binary pulsar system. Until then, there is no such a thing as such a thing. They believe that binary pulsar system is existed. So they are so excited, and they did some observations up to a decade. After that much research on them, the binary pulsar system, they got an unusual report that they observed a gradual decrease in the orbital period. I said that these are like cosmic clocks, so they don't change at time because of there is no like resistance to them. But they too see they observe a gradual decrease in the orbital period. Why they calculated something like 75 microseconds per year, and they doubted that why is this actually happen, and they remember Einstein. Einstein said that there are gravitational waves coming from the when two bodies accelerated together, and that's how they releases some energy, and that's the decay of the orbital period. They did the both calculations of the uh, like binary pulsar systems decay and Einstein's predictions, and shockingly, the decay matches exactly to the predictions of Einstein. This is the indirect proof of gravitational. It is not direct because they didn't find the like directly they didn't find the gravitational waves, but they find that gravitational waves may exist. So the discovery and the both the 1993 Nobel Prizes in physics. Okay, the next thing, there are two parts over, and the next thing, the first direct detection of gravitational wave. First thing, we will learn about first direct detection by LIGO, the gravitational waves by LIGO. We will learn more about LIGO in few minutes. First, how to detect gravitational waves. There are two main methods to detect them. First one is by resonance, by using aluminum bars. Sorry, okay, by using aluminum bars or Weber bars. The second one is by measuring length. The change in length, to be accurate, by measuring the change in length. We will learn it. First one, by using resonance. This is the first attempt to find the gravitational waves. This is done by Joseph Weber. Like we can see him in the picture. He is using the resonance concept. We know that every body has its natural frequency and vibration. Like if the body will, like if we introduce it to a same frequency wave, if we take 144 hertz like toning fork, and if we like maybe you see them in the laboratory or some YouTube videos, when the same frequency comes near to it, it will vibrate with some more amplitude because of the resonance that is called as the resonance. That's what he thought. What he tried to do is he took some aluminum bars, and someone called as Weber bars after his name, and placed them in a vacuum tube and vacuum chamber, and leave it. Just wait, because we know the natural frequency of the aluminum bar, but when we observe the when we observe the amplitude increase, when the resonance will observe is when a gravitational wave with the same frequency hit it. He tried it, but there is no such results came because the gravitational waves are so weak. They have the frequency, but the amplitude of gravitational waves is so much weak, extremely weak. Like the strain is about 10 power minus 21. It's a so much small, like smaller thing. So that's why we can't, he can't detect them using this method. But it is a very popular method, and that's it. The next method, it is our now present method. It is best method for measuring, and it is by measuring the change in length, not length, by changing length. We know that matter will stretch and squeeze. I told you to remember that matter will stretch and squeeze as gravitational wave passes through them. Like here on the foot image, we see that when gravitational wave is at its peak, it will stretch or squeeze according to that. We can how can we measure that? Then we can measure the change in length. If we can measure the change in length of a object, then it is like saying that it is a detection of gravitational wave. The main problem is how to measure the length, or how to measure the change in length. uh, Anybody has any idea how to measure it? Okay. Like someone says that if we take the traditional method, like measuring with a tape or measuring with a scale or anything, it won't work. Why? Why the scales? Why can't we use scales in them? Because if we want to measure a bar, aluminum bar or anything, and we have a scale with the length more than a bar and we are measuring it, and what happens when a gravitational wave passes through is the scale itself compresses and expands or stretches or squeezes according to the bar, and like it is also compresses and squeezes with the bar also, so we cannot measure the change at all. That's why we can't use scales. So we need a thing that doesn't change according to the space-time. So what is it? Any guesses? That doesn't change. Yeah, I'm saying it's the speed of light. Again comes the Einstein. He said that is there anything that doesn't change according to space-time? Is only speed of light. Speed of light is absolute. It doesn't change according to the frame of reference or anything. It doesn't change. So the idea is to use the speed of light or light, we can predict that the change in length. That's how the starting of LIGO comes in. LIGO in 1970s, near 1970s, some scientists come up with this idea. Like I said, it uses light to calculate the change in length. So light is cannot change. So we can use it to change, like we can use it to measure the change in length. LIGO means laser interferometer gravitational waves observatory. We will learn what is like we learn the gravitational waves and we know that observatory what is it. We learn interferometer after these slides. So and after the scientists proposing the project at around 1970, the first direct detection of gravitational wave is done on 14th September 2015 at 9:50:45 UTC and named as GW150914. Uh, if we observe GW15 means 2015, 09 means September, and 14 means 14. They are almost every gravitational wave they detect, they name like this. And the detection was made almost a century after the Einstein's prediction. Einstein predicted that on the 1916, this was detected on 2015. Like next, we are going to see about this what signal, what signal they receive. The signal is come from a binary black hole system at 1.3 billion light years away. These two black holes are 29 and 36 solar masses. And after the combined black hole has at around 62 solar masses. You guess when we did some math, 29 plus 36 is 65. But what about what happens to the remaining? What happens to the remaining three solar masses? Any guess? Like for those three solar masses, those become energy in the form of gravitational wave. I said gravitational waves carry energy. This is where the energy comes from. Two black holes, when two black holes or pulsars or otherwise any when I so these two merges, then they will release energy in the form of gravitational wave. That energy came from the famous equation E equal to mc square. The mass of the gravitation, like the mass of the black hole, will convert into energy in the form of gravitational wave. And the signal only lasts for 0.2 seconds. But the fun fact is, not fun fact, the fact is, at the peak of the power radiation releases from the black holes, it is more than 50 times of the power of light comes from all over the universe. All the stars, all the like pulsars or everything, all the universe's light combined and multiplied by 50 times. That's how much energy releases when a black hole measures or gravitational waves releases. Okay, that's for the signal. And finally, this discovery confirms the Einstein's prediction of gravitational wave. They calculated it, and the predictions are exactly confirmed, exactly same with the Einstein's predictions. And it also confirms that binary black hole systems are existed. Like until then, they didn't believe, like the previous situation, they didn't believe the binary pulsar system is existed. So like that, until the detection, we didn't believe that there are binary black hole systems are existed. And these three persons, these three scientists, Rainer Weiss, Barry C. Barish, and Kip S. Thorne, were awarded by 2017 Nobel Prize in Physics for decisive contributions to the LIGO detector and observation of gravitational wave. Okay, that's it from my side and the historical journey of the gravitational waves and the first detection of LIGO. I will hand over it to the Asim to say about next thing, how the LIGO works, and that's it.
Hi fellows, so Avinash mentioned the term LIGO. In this part of our presentation, we are going to see what is LIGO. Yes, you read right. If you currently are laying on your couch, it's not your fault. It's the freaking gravity. That was just a joke. LIGO actually stands for Laser Interferometry Gravitational Wave Observatory. Observatory is a place where we have set up to observe something. And I'm going to show you a drone view of the actual setup, an observatory which is installed in US. Yes, this is huge. The arms that you can see in the form of pipes are 4 kilometers long, and there are two of them only in US. Now, you are hearing the term gravitational waves from the start of the presentation, and everybody's saying gravitational waves causes distortion in the fabric of space-time. But how exactly it happens? Let's try to understand it. And I have a very easy example to show you. Now imagine you have a table of square shape and a gravitational wave is coming right above from the vertical direction. Now what will happen? How the shape of that square table will change? Well, so focus on two adjacent sides. One of those two adjacent sides will stretch and the other one will squeeze at the same time. Now with the parallel sides of that square, the same will happen. So this squeezing and stretching pattern will happen alternatively and the speed of which will depend on the frequency of gravitational wave. Now I have a demonstration to show you. Yes, this is a square table that we were imagining and see how the distortion happens. Now, we saw how gravitational wave distorts space-time curve and we know what an observatory is. But the initial part of LIGO, which is laser interferometry, I suppose we all are familiar with laser lights. But what is interferometry? Interferometry terms comes from interference. Now we are going to see and have a quick recap of what is interferometry. So these are two light waves. The one at the top is shown in the red color, and the middle one is in blue color, and the bottommost is the resultant when you add those two light waves. Now, in these two light waves, which are going to be added, their crests and troughs have the same position. That's why when you add them, the positive extremes and negative extremes gets added, and the resultant amplitude increases to the maximum. Now, what will happen if you shift one of those with respect to the another? The resultant amplitude will decrease, obviously. See this picture? Here the amplitude you can see has been decreased because you have shifted the blue wavelength. Yeah, one more important thing, these two waves which are being added are coherent. That means both have same frequencies. Now when you shift the blue wavelength a little forward, then the crests and trough are de-aligned. That's why they lead to a lower resultant amplitude. Now, in the same way, if we do it a little more, I mean, when you add the crest of one wave with the trough of another one, what will happen? The positive extreme will get added to the negative one, and that will result in zero amplitude of the resultant wave. See this picture? This is exactly what I was talking about. Now, this is interference, and we use these interference patterns in laser interferometry. We are going to see what is laser interferometry with the help of the actual setup we use in LIGO. This is the setup where the cylinder depicts laser light and it emits a parallel laser beam, which is very strong because we want more accuracy. And we introduce a circular surface in the path of that laser light, which is partially reflecting and partially transmitting. Now, this introduced surface splits the main laser beam in two orthogonal beams. Now, why are both of the split beams are orthogonal or perpendicular? So the reason is the angle between the main laser beam and the introduced surface. Now you can see it more clearly in this slide. Yes, so the angle between the main laser beam emitted by the laser light and the surface, which is called beam splitter, not surprisingly, because it splits the main laser beam into two minor beams. So the angle between those is 45 degree, which leads to the perpendicular distribution of minor laser beams. Now, when this distribution happens, we let these splitted laser beams travel to a long distance in space, after which we introduce some reflective mirrors. That is one reflective mirror, which is 100% reflecting in each of the paths of splitted laser beams. Now, these reflective mirrors reflect the light coming from the beam splitter in the same direction which was through which the incident light came. Now, the light beam, after reflection following the same path on which it came from the beam splitter to the reflective mirror, following the same path, it comes again to the beam splitter, and after reflection or transmission, it gets to the surface that you can see, which is shown in this picture as a square 2D plane. Now here we see the same thing that we discussed in the interference patterns. Here two light waves collides with each other, and we get to see an interference pattern. In the original setup, we fix the path lengths of splitted laser beams in a way that they interferes destructively. That means crest of one wave interferes with trough of another one, which leads to dark fringe formation on the surface. Now, we saw how any change in the path of these spirited laser beams will cause a change in interference pattern. And this is exactly what scientists take as a cue that a gravitational wave has passed through our setup. Now imagine you change the position of one of those reflective mirrors. Then the path length upon which the light has traveled all the way from laser light to reflective mirror and to the beam splitter again and finally to the surface. So the path will change and that will create a difference between the phase. Phase is the angle, or better if I do not introduce the phase term, you can just imagine how we shifted the two beams in the interference slide and the pattern, that the resultant amplitude of the final added light vector gets changed. So this change is what we get as a cue that a gravitational wave has passed through our setup. Now, how exactly it happens when a gravitational wave passes? So I have a slide that will make it very clear to you. We saw how gravitational waves change the shape of a square table in the fabric of space-time. Now let's see, in the original setup, both of these LIGO arms, which are the path on which splitted laser beams travel, both of these arms have almost equal length. That's why if you see it from above, it can be understood as two radiuses and you can form a circle, meaning from one reflective mirror to the another one. Now how this will change when a gravitational wave passes through it? See this slide. A gravitational wave is shown by h with respect to time, and the two red lines are the LIGO arms. The green semicircle is the laser light, and the blue rectangles are reflective mirrors. Now we are seeing the LIGO setup from right above, and a gravitational wave is passing right above from the zenith. Now, what will happen? You can imagine just in the pattern, the shape of our square shaped table changed. One of those adjacent side will squeeze and the another one will stretch at the same time. This is exactly what happens. Now, this happens alternatively with both of these LIGO arms, and this is what causes the change in interference pattern. Now, until now, you have a clear understanding of how LIGO works. But for your information, I have to tell you a fact that the concept of this interferometer, which is called Michelson interferometer, I'm talking about this setup. Yes. So this idea came in around 1970s, and the actual detection can be made in 2015. Now, why did it take around half a century to practically implement an idea like this, which is seeming so simple to you? Now, we will see, after a summarization of what we have studied till now. Yes, the first point, which is noteworthy, is we have to evacuate the whole path through which laser light is traveling. This means here you can see there are perpendicular paths on which light beams are traveling. Now we want very great accuracy and precision, and that's why we don't want light waves to interfere with dust particles or air particles, which will distract them. And we want strengthened and powerful laser beams. That's why we have to evacuate the whole path, and this is something which makes this project very expensive. Now the next point is Yeah, in original configuration, the pattern, interference pattern is destructive, as we discussed about it earlier. And yes, this is something which is also noteworthy, that the gravitational wave which causes distortion in the fabric of space-time have a level of strain in order of 10 to the power minus 21, which is very, very less. And this is exactly the point which explains why did it take half a century to actually implement the idea of Michelson interferometry to a practical level. Because we need marvelous level of accuracy to actually measure a gravitational wave of this very, very low strain level. Now, generally, if you implement the normal idea, gathering normal equipments, then your errors will outweigh the actual gravitational measurements. And this is the reason you won't be able to measure actual gravitational waves, and you can't rely on that. Now, one thing that I need to explain, what does this mean? The strain is in order of 10 to the power minus 21. It's very less, I get it. But what exactly the mathematical meaning of this is? Well, so imagine a gravitational wave which is passing through Earth has a strain level of 10 to the power minus 21. Now, and you have a 1 meter rod which is lying in space, obviously. Now the stretching and squeezing of this 1 meter length will happen on in the order of 10 to the power minus 21 meters. And to increase the accuracy of our LIGO setup, we use 4 kilometer arms. Now imagine what will be the visible change in the length of LIGO arms. Since 1 meter rod has a 10 to the power minus 21 meter of visible change, a 4 kilometer arm will have 4,000 multiplied by 10 to the power minus 21 meter. Now, wouldn't it be better if we increase the arm lengths to millions of kilometers? Obviously, it will be more accurate and it will give us more precise measurements of gravitational waves. But the thing is, we can't do this. We don't have so much money to spare on a project. And that's how we come up with an engineering tactic which increases the path length without actually increasing it. This is something called the concept of Fabry-Perot cavity that we will discuss now. Yes, these are this so that we have two more mechanisms which increase the accuracy, and these are the systems that have been installed in advanced LIGO. Advanced LIGO is the LIGO setup that we are currently using and which is practically able to measure gravitational waves which are reliable. Now, one is pendulum suspension and another one is Fabry-Perot cavity that I mentioned. We are going to discuss both one by one. Pendulum suspension is something that is very easy to understand. Now, why do we use it? So imagine you are an engineer working around LIGO setup and you sneezed. As I mentioned, gravitational waves have a very, very low strain level. So even your sneeze will cause greater vibrations in the reflective mirrors than that caused by gravitational waves. So you need to be prepared for that, and we somehow have to isolate the mirror vibrations from external setup vibrations, and this is we do by connecting the mirrors to the external setup via silica fiber ropes. Why do we use silica fiber ropes? Because it's very strong and the mirrors weigh almost 40 kilograms, and we want the rope to be very thin. This is something which you will understand when you go into the engineering details. Now, you can easily visualize how this connecting rope will act as a pendulum when the external setup vibrates, and it helps the mirror to maintain a stable position. Now, there are a lot of reasons which causes these kind of vibrations in the external setup. One is seismic vibration, which is caused by earthquakes, and one is thermal vibration, which is present in each and every object existing in universe which have a temperature. Now, you filter these external vibrations from reaching it to the reflective mirrors used in our setup. But this filtering is not very effective if you do only using a single suspension model. What is single suspension model? That you used pendulum only to one level. See the next slide. Here we have used four levels of pendulums, and this gives an a more effective suspension of mirror vibrations from the external setup, and that's why we use this. Quadruple name is not very surprising since these contain four level of pendulum suspension. This is called a quadruple suspension system. What is the sensor actuator written in this slide? Well, so I said there are a lot of reasons which causes different kind of vibrations in the external setup. So even after filtering it with the help of a quadruple suspension system, there is some tiny vibrations left in our reflective mirror used. We need to filter these as well, and that's why we use sensor actuator system. And one thing which needs to be mentioned, at last there is something called as radiation pressure. So you can see there are reflective mirrors, which is shown by black circles, and when the splitted laser beams hits the reflective mirrors, and we know that light carries momentum, so there will be some momentum exchange between light and the reflective mirrors, which will cause some vibrations as well. And we can isolate this with the help of suspension systems. That's why we take help of sensor actuation system. This is a feedback mechanism. What is feedback mechanism? See, we set an electrical setup uh, in the suspension system which measure what are the final vibrations left in the reflective mirror, and the system converts these vibrations into electrical signals and generates a counter vibration, which is again sent to our suspension system and creates a counter vibration which cancels out the actual vibration present in the reflective mirrors. And this is something which makes the suspension very effective. This is all about quadruple suspension system. Moving to Fabry parrot cavity, in this thing, we introduce a new mirror in the path between beam splitter and the reflective mirrors. Now it happens when light, after being splitted through the through the beam splitter, the light passes through the new introduced mirror and it hits the reflective mirror in the usual manner it used to do. Now, when it comes again to the beam splitter, the new introduced mirror prevents it to go to the beam splitter and reflects it again. Now, this reflection causes another reflection through the reflective mirrors, and these reflections happen 300 times between these two mirrors, and after 300 times it passes through the new introduced mirror and goes to the beam splitter. Then through the same process it reaches to the surface and creates an interference pattern. Now imagine what we have done. We made the light travel 300 multiplied by 4 kilometer lengths, and this is what effectively increases the arm length. This is exactly what we needed when I mentioned gravitational waves has a very low strain and bigger arm length is better because it will lead to a greater visible change in the interference patterns. Now, this is all about the fabric parrot cavity installed in a LIGO setup. Let's have a closer view about this fabric parrot cavity. Here are these two mirrors, and there is an input beam which hits the first mirror and passes through it. Now, through the second mirror, it can't pass and it gets reflected. Now, reflection between these two mirrors happens again and again, and how many times it will happen depends on the characteristic of this fabric parrot cavity. Now, after a certain number of times, it gets emitted through the second mirror. Now, this is all that we had to discuss in this part of our presentation. Now, one thing that I'm giving you all as a homework is first have this information that the mirrors used in LIGO setup has a reflectivity of 99%, which means it will reflect the 99% intensity of the input beam and only 1% would pass through one single mirror. But in fabric parrot cavity, which we use in LIGO setup, has an in output upon input ratio equals to 1. Now, how does this magic happen? So just consider light as waves and calculate the output upon input ratio as taking the distance between these two mirrors as a parameter, and then it will just be one page of mathematical calculation and you will get how this magic happens, i.e. how output upon input intensity ratio equals to 1. Now Rachna is going to talk about the futuristic concepts and what are we planning to modify in LIGO setups. Rachna.
So yeah, hi, this is Rachna. So all right, so far we have seen what gravitational waves are, how we detected them, and what they have told us about black holes, neutron stars, and the very fabric of space-time. But we are still only scratching the surface here. So let's pause for effect and let's flip the telescope around. What will gravitational wave tells us in the future is what we are going to see about. What mysteries are still holding in the cosmic static. So what you're about to see is not just a bunch of new detectors. It is the start of a whole new chapter in how we understand the universe. So we are talking about listening to events that happened billions of years ago, peering inside neutron stars to decode the laws of matter under extreme pressure, and maybe even catch faint ripples from the Big Bang itself. But to get there, we need better tools, bigger detectors, quieter environments, and entirely new frequency bands that no ground based mission can reach. And that's where LISA, LIGO India, Kagra, and Pulsar arrays come in. So, along the way, I'll walk you through the physics behind these detectors, like strain sensitivity, quadruple radiation, chirp mass, tidal deformability. But wait, I promise it will all make sense because the math is what helps decode the signals. So let's fast forward into the next decade of gravitational wave astronomy and explore what we will hear, what we will learn, and how close we might be to answering the deepest questions of the universe. Because this isn't some sci fi movie, this is the 2030s of astrophysics. So the global gravitational wave network, this is expanding really fast. Each new detector brings something unique, like Virgo's improved tech or Kagra's innovative cryogenics, and soon India joins a frontier with LIGO India. Most revolutionary is LISA in space. With massive arms, it will detect low frequency waves that earthbound detectors can't hear. Now, a question for you guys. Why do we need gravitational wave detectors in different parts of the world? Why are we not just sticking with one? Anyone can answer just in that in the chat here. Like, why are we not just having one detector? It's actually to triangulate the source because when a gravitational wave it passes through Earth, the time delay between the detectors it helps us locate the direction it came from. Like how GPS uses timing to locate you from your from your final destination. This is similar to that. More detectors is equal to the better sky localization and faster alerts for telescopes. Now, Virgo, Kagra, LIGO India, each detector is like different camera angle of the same scene. But here's the twist. Imagine you're trying to film a firefly from 10,000 kilometers away. And that's where LISA comes in. It is the telephoto lens in space with arms so long it can catch even the slowest and faintest flutter in space-time. And of course, the bigger your lens, or in this case, the interferometer arm, the finer the signal you can detect. And that brings us to the next question. Why do we need long arms? Basically, strain, which is nothing but the fractional change in length, is tiny, which is often less than 10 power minus 21, as already Asim mentioned. Now, the longer the arms, the more detectable this minute stretching becomes. Now, LISA's immense arm length and space environments make it capable of detecting much fainter signals than ground-based setups. Now I have shown a diagram here. Basically, this diagram compares the sensitivity bands of two major gravitational wave detectors, which is LISA, the laser interferometer space antenna, and LIGO, the laser interferometer gravitational wave observatory. Now, what you see here is the y-axis is nothing but the gravitational wave amplitude or the strain, or in more simpler words, the strength of gravitational wave signal. And the x-axis, that will be the frequency that is measured in hertz, which is nothing but the frequency of the gravitational wave. So what the diagram shows is basically list of the sensitivity band. You can see in the left side, the blue shaded region. The frequency range is going from 10 power minus 4 hertz to 1 hertz approximately. And resolved galactic binaries or the coalescence of massive black holes, LISAs detect these low frequency waves which are inaccessible from the ground due to seismic noise, which is already mentioned by Asid. Now, LIGO, which is the right-sided, the green shaded region. Basically, the frequency range, it goes from 10 hertz to 10 power 4 hertz. And, the neutron star coalescence or black hole or supernova core collapse, those produce such high frequency gravitational waves which are detected by LIGO. Now, why do we need both LISA and LIGO is because basically they just complement each other. Like LISA, it captures the early in spirals and massive events in deep space, whereas LIGO captures the final mergers of the compact stellar objects. So some systems could be observed first by LISA and then later by LIGO. So basically for multi-band observation, to simply put. So the strain, so for better sensitivity, we are just increasing the arm. That's it, in simple words. Yes, each detector type listens to a different part of gravitational spectrum. Like how we have light spectrum, similar to that. LISA will pick up much heavier and slower moving systems, while pulsar timing array, that might reveal the deep rumble of ancient cosmic structures. So the pulsar timing arrays here, what they use is basically the multi-second pulsars. That is nothing but the cosmic clocks, which is already dealt by Avinash. Basically, they detect very long wavelength gravitational waves. So supermassive black hole binaries at the galaxy centers, they will produce such gravitational waves. Now, LISA and LIGO we have already seen. Now, why do we need all these three? Is basically together they cover 14 orders of magnitude in frequency. So, it allows for a multi-band gravitational wave astronomy, much like observing light across radio, optical, and X-ray bands, similar to that. This is just gravitational wave spectrum, not light. Fine. Now, with this detection here, we didn't just detect space-time ripples. We saw the flash of the kilonova, measured heavy elements being born, and even used it as a cosmic ruler to estimate how fast the universe is expanding. And obviously, more about the first detection and how the detection is done is already covered by both Avinash and Asim. So I'll just go to the next slide here. Yes, this is where things get interesting. Let's just take a closer look at the actual maths behind how gravitational waves are produced. So, according to general relativity, accelerating masses distort spacetime, and in certain conditions, they radiate that distortion outward as gravitational waves. But there's a catch. Not all accelerating produces gravitational waves. For instance, perfectly spherical explosion, no waves. A mass which is moving in a straight line, it will still produce no waves. So what does produce waves is basically when the mass distributions change in an asymmetric way, specifically when there is a changing mass quadrupole moment. Whoa, that was a big one. So what is that? The mass quadrupole moment is a measure of how lopsided a system's mass distribution is. It's like a second order generalization of the dipole moment in electromagnetism. But since mass is always positive, there is no gravitational dipole radiation. So quadrupole is like the leading order radiation. And here I have given the key formula. Let us just forget about all those constants here and just focus on h being directly proportional to d2q by dt squared. Basically, the gravitational wave strain h here is proportional to the second time derivative of this quadrupole moment. Basically, how fast the mass configuration is changing. That's it. So if you want a really strong gravitational wave, you would need lots of mass moving really fast in a non-symmetric configuration. That's it. Only three conditions. And that's why binary systems like black hole, or neutron star binaries, they are the perfect gravitational wave factories. They have huge masses and they orbit each other at a significant fraction of the speed of light. And their configuration, it changes rapidly and asymmetrically. And imagine as they spiral inwards due to energy loss via gravitational radiation, their orbits shrink. And the frequency and amplitude of the gravitational wave increases, creating the famous chirp signal that detectors like LIGO pick up. So this single equation right here, the quadrupole formula, is at the heart of how we connect Einstein's theory to real observable signals, which is basically the starting point of multi-messenger astrophysics. Now we go to the next one. What you're seeing on the screen is what we call a chirp, the signature gravitational wave signal from a binary system like two neutron star or black hole spiraling into each other and merging. You would have already seen it's quite famous, the waveform which increases the amplitude and the frequency increases. Basically, the signal starts off at low frequency and low amplitude, then it increases in both frequency and strength as objects get closer, much like the rising pitch of a bird's chirp, and that's where the term comes from. Now, at the heart of this waveform is a crucial quantity called as the chirp mass, which is denoted by m right here, this formula. It is a specific combination of two masses, m1 and m2, that completely determines how fast the frequency and amplitude grow as a system evolves. Now, why is this even important? It's because the rate at which the frequency increases, that is, how steep the waveform becomes, is directly related to the chirp mass. So, by measuring the waveform, we can calculate m very precisely. In fact, the chirp mass right here is the best measured parameter in any gravitational wave signal. So, once we know m, we can also work backwards using additional features of the signal to try and extract the individual component masses, which is m1 and m2. Now, that's what allows us to say things like, you know what, this event was a 30 solar mass black hole merging with a 35 solar mass black hole. The chirp mass basically controls the rate at which the waveform rises in pitch and intensity. So by analyzing this pattern, scientists can reverse engineer the masses of the merging objects. The gravitational waves encode how much a neutron star deforms before merging. Now let's imagine two neutron stars spiral towards each other. they begin to tidally deform, just like the moon pulls Earth's ocean, but not exactly. This deformation depends on what is inside the star. So, a star with soft equation of state is more easily compressible. So, it distorts more and merges sooner. And its gravitational wave signal has a sharper cutoff. Whereas a stiff equation of state that makes the star resist the compression. It holds its shape longer, and this stretches out the late stage waveform and show longer gravitational wave tails. Now for better visualization. Imagine dropping two marshmallows into each other, okay, versus two steel balls. The marshmallow, they deform, squash, and splatter early. And the steel balls, obviously, they resist, bounce around, and then merge with a thud. Right. So that's what we are seeing with gravitational waves from neutron star collisions. The signal shape and tells us what is inside these stars, either marshmallow-like nuclear fluids or exotic ultra-stiff matter. So by analyzing this behavior in gravitational waves, we can estimate a quantity called as tidal deformability, which is denoted by lambda, the formula right here. Basically measures how easily a neutron star gets squished by its companion's gravity, in simple words. And from that, we can infer the equation of state, which is like the holy grail of nuclear physics. Now, it tells us if the core is made up of neutrons or hyperons or quark matter or something even stranger. Right. The 2030s will see us move from detection to precision gravitational wave astronomy. With Einstein's telescope and cosmic explorer, we will peer deeper into space and time than ever before, tracking black hole formation histories and probing cosmic origins. Now, that's a meme right there for you guys because gravitational wave physicists, they just don't do simple stuff. Okay, so whatever you're seeing there in the slide, those four questions, I just came up with those four, but there are a lot more. These aren't just big questions. They're literally the blueprints for the future research. And each mystery is a doorway to deeper understanding. And gravitational waves, they are the key that unlocks them. So that's it from my side. Thank you. And over to Kishle.
Thank you, Rachna, for the wonderful presentation. Now we'll ask Mridula and Rohit to say last words for the summer schools and all. Mridula and Rohit, you can carry on.
Okay. Hello, everybody. We have come to the end of summer school session. So we had 5 sessions, and this was our last. And all the speakers did a very good job. And thank you for the audience to patiently listening to us. And I hope this was a good learning journey. If you have any suggestions or if you have any questions, you can ask here, or we'll send a feedback form. You can post your questions or queries over there also. And regarding the assignments and drives, we'll soon post a drive link, so you can look over the resources and the presentation we have used in all the 5 sessions. Yes. Now, if you have any questions or queries, you can ask here too. Yes. Thank you. So, Rachna, you can stop the streaming part.